Welcome back. Today, we finish our introductory chapter by giving you some information on ceramic products and applications. Ceramics are used for a broad range of applications which are related to one or more properties or functions, such as optical, thermal, electrical, magnetical, nuclear, chemical, biological, and mechanical. Let's have a closer look at each group. Starting with optical functions. Ceramics might be opaque, translucent, or transparent, depending on the amount of light that is transmitted through them. Translucence is required, for instance, for orthodontics applications to resemble natural teeth, like dental porcelain. Transparence is a key parameter for light transmission in optical fibers, as silica. Other ranges of the radiation spectrum may be also applied, e.g., infrared transparency in laser windows made of calcium fluoride, cesium iodide, potassium bromide, potassium chloride, or sodium chloride, which are all considered ceramics. Thermal functions are related to high or low conductivity. Typically, high thermal conductive ceramics such as aluminum nitride are used in substrates for electronic applications, and thermal insulators of cordierite, for instance, are used as kiln furniture. Curiously, a single ceramic material as alumina might present either high or low conductivity. The reason lays on the amount of porosity, particularly non-connected or closed porosity. The entrapped air in the pores is responsible for the insulating character of alumina bricks or plates. Moreover, thermal conductive boron nitride can be used as cooling fillers for insulating plastics and adhesives. Regarding electrical functions, we have as well a broad range of conductivities. Covalent-bonded ceramics such as silicon carbide or molybdenum disilicide are mostly semiconductors and may be used as heating elements in resistive furnaces or kilns. Otherwise, ceramics are mostly electrical insulators such as porcelain, aluminum nitride, or alumina. The later ones are used as substrates for electronics, for instance. Piezoelectricity refers to the phenomenon of transforming a pressure signal into electricity, or the other way around, such as in the case of sensors and ultrasound generators, respectively. PZT, lead zirconate, titanate, and barium titanate are examples of piezoceramics. Fluorides are iron-mixed oxides that might be used as permanent or hard magnets in loudspeakers and temporary or soft magnets in electrical transformers, for instance. A complex oxide based on yttrium, barium, and copper was found to be a superconductor, allowing electricity to pass through with no resistance. Nuclear or atomic energy plants rely on many parts that are made of ceramic materials, as fuel pellets of uranium dioxide and neutron absorbance or reflectance parts, respectively, of boron carbide and beryllium oxide. Ceramics are important in many chemical processes due to their corrosion resistance as well as their inertness at higher temperatures. They can be found as cordierite catalyst supports, as porcelain labware, or membranes for water and wastewater separation, made of alumina or silicon carbide. Due to their chemical inertness and biocompatibility, ceramic materials are widely used in medical applications as implants, repairs, and restorations. Some examples are hydroxyapatite, beta TCP, or bioglass for bone reconstruction, and zirconia toughened alumina for replacement of hip, knee, or shoulder joints. Last but not least, mechanical properties are always relevant in any application. In some products, a specific mechanical property is required. For instance, hard materials such as silicon nitride or alumina are used as cutting tools for metal machining. When a high wear or abrasion resistance is needed, alumina or zirconia wire guides are employed in the textile industry. The impact resistance allied to a low density is the key parameter for vehicle and body armors, which include materials such as alumina, silicon carbide, and boron carbide. Finally, many ceramic parts are used as seals and bearings, which need to be hard and tough, like silicon carbide and silicon nitride. Dental restorations such as crowns, bridges, and veneers can be made from feldspatic porcelain, as well as lucite or lithium disilicate glass ceramics and zirconia. Those materials are suited for shaping by pressing or machining and available in several degrees of translucency. Optical fibers are flexible, transparent fibers made of silica, which are used to transmit light in fiber optic communications at higher data transfer rates than electrical cables. Single-mode fibers are designed to carry light energy on one path over long distances with a core as small as 8 microns in diameter. Multi-mode fibers have a larger core measuring up to 62 microns in diameter and are built for light signals that must travel many different paths simultaneously, usually over shorter distances. Optical crystals are applied in infrared windows and optics used in infrared spectroscopy, typically made of calcium fluoride, cesium iodide, potassium bromide, potassium chloride, or sodium chloride. Electronic circuit carriers may be manufactured from aluminum oxide or nitride. They are characterized by their high thermal conductivity and low electrical conductivity, as well as high mechanical strength. Ceramic substrates are suitable for thick and thin film applications. Pieces of kiln furniture are used as supports for firing, sintering, and other heat treatment processes at temperatures over 1000 degrees C. They have many variations in either size, shape, material, or all these combining factors. They can be made of cordierite, alumina, or silicon carbide. They are refractory materials, which must resist to thermal shocking and present low creep rates. Boron nitride cooling fillers are engineered to line up easily and to form bridges that conduct heat in the direction of their orientation, which can be made either horizontal or vertical. Silicon carbide or molybdenum disilicide are used as heating elements in many electric furnaces, as well as in other electric heating devices. They are characterized by long stability at high temperatures with minimal deformation. Both traditional ceramics such as porcelain and advanced ceramics such as alumina or aluminum nitride are inherently strong electrical insulators. A wide range of electrical insulator components may be manufactured in various shapes and sizes, providing high electrical resistivity, dielectric strength, and other application-specific requirements. Piezoceramics such as PZT, lead zirconate titanate, are used to convert mechanical parameters such as pressure and acceleration into electrical parameters or Conversely, to convert electrical signals into mechanical movement or vibration. They can be used in ultrasonic transmitters and receivers, as well as in precision positioning or injection systems. Ferrite magnets are made by mixing and firing iron 3 oxide blended with small proportions of barium, manganese, nickel, and zinc. They can be divided into hard or soft ferrites. Hard ferrites are difficult to demagnetize and are used in permanent magnets for loudspeakers and small electric motors. Soft ferrites easily change their magnetization and are used in inductors, transformers, antennas, and microwave components. Many possible applications of the so-called high-temperature superconducting materials have been discussed, such as magnets in magnetic resonance imaging and magnetic levitation. In the case of yttrium barium copper oxide, superconductivity happens at relative high temperatures, around 93 Kelvin or minus 180 Celsius, which is above the temperature of liquid nitrogen. The fuel pellets used in a nuclear reactor are made of uranium dioxide. The fuel pellets are enclosed in rods. A typical reactor contains 45,000 fuel rods. Ceramics are also used as seals and valves, as well as for encapsulating radioactive wastes for long periods of time. Hydroxyapatite, beta-TCP, and bioactive glasses are available in a range of sizes from 10 micrometers to 1 millimeter and can be in the form of spheres, rounded or irregularly shaped particles, and cellular scaffolds. Those biomaterials are increasingly used for bone grafting as well as dental restoration. Advanced ceramics such as ZTA, zirconia toughened alumina, are biocompatible and bioinert. Moreover, they present high hardness and smooth surface that minimize wear, leading to a lower risk of infection and to fewer complications in replacements of hip, knee, and shoulder joints. To fabricate an automotive catalyst, a slurry containing the catalyst components, precious metals such as platinum, palladium, rhodium, is applied to the cells in a cordierite honeycomb to form a coated layer. The toxic substances and exhaust gases as hydrocarbons, carbon monoxide, and nitrogen oxide are transformed into harmless nitrogen, water, and carbon dioxide by the action of the catalyst. Labware include mortars and pestles, boats, crucibles, cups, dishes, among many other products. They are produced in a variety of ceramic materials ranging from porcelain to alumina and zirconia. Ceramic labware are chemical resistant as well as hard, thermal shock stable, and refractory. Alumina hollow fiber and silicon carbide flat membranes are used for water and wastewater treatment. They have high chemical resistance in extreme pH ranges and oxidant environments, besides high flux rate. Inserts for metalworking can be manufactured from silicon, silicon nitride, cubic boron nitride, or oxide ceramics. They are used for turning, grooving, milling, and boring in a wide variety of industrial applications due to their high hardness, toughness, and chemical stability. Ceramic parts can be used in the production of textiles as bushing, thread, and wire guides. They present high heat and wear resistance and a low friction coefficient. Common materials employed are alumina, zirconia, silicon nitride, and silicon carbide. Ceramics such as alumina, silicon carbide, and boron carbide offer many advantages over conventional materials for vehicle and armor applications. such as low weight and high hardness, with proven performance for ballistic standards. Silicon carbide mechanical seal rings are effective for applications where wear and corrosion resistance are critical concerns. Silicon nitride wear components are used as seals and bearings in aircraft engines, hydraulics, and fuel systems. To finish our introductory chapter, let's talk briefly about material selection. Ceramics are materials with an impressive capability to hold their properties under extreme environments, requiring excellent mechanical, chemical, electrical, and thermal wear resistances. Other materials may excel in one area, but ceramics uniquely combine high performance properties for demanding applications. There are different approaches for selecting materials. A useful method is plotting material property charts, sometimes called Ashby charts, with one property on one axis and another property on the other, both in logarithmic scales. In those charts, materials groups are merged, with all the ceramics, for example, having similar values. They can be used to perform material selection for new designs or to identify trends in properties and the relationships between them in a highly visual way. Let's now skip for some exercises. Please try to answer the next questions using your own words. Nevertheless, cite the references for specific data or images that you will eventually use. Questions. Explain how porosity can influence transparency, conductivity, and strength in ceramic materials. What is the best combination of thermal and electrical conductivities for a ceramic electronic substrate? Comment on 3 different types of porcelain regarding their composition and application. Why the use of high-temperature ceramic superconductors is not so widespread in terms of practical applications. Discuss some environmental or health issues related to the use of beryllium oxide. Which combination of properties is expected from ceramic materials used as cutting tools? Why ceramics must be combined with other materials in a body or vehicle armor system? Why optical fibers made of brittle silica glass can be bent without breaking? How can a piezoceramic material be used for producing electrical energy? Use an Ashby chart to justify the choice of technical or advanced ceramics as high Young's modulus materials with a low negative environmental impact. That's all for today. Thanks, and see you next time.